Hey, welcome. You can follow along with a piece of code, line by line, and still not really get the intuition behind it. Today, we're going to fix that. We are going to rebuild the very brain of a neural network, right from scratch, from absolute first principles. The goal? To build that deep, gut-level understanding of how these things actually learn. All right, here's the game plan. We're going to start with a really simple question, what I call the problem of influence. Then we'll literally invent a language to talk about it. From there, we'll assemble a neuron, put it into a learning loop, and then, this is important, we'll see where it all breaks. And finally, we'll look at the road ahead. Sound good? Let's dive in. Okay, section 1, the problem of influence. And I really want you to do something for me here. Forget everything you think you know about neural networks. Just for a second. We're going to start with something way, way simpler. A single, basic math expression. So here it is. L equals A times B plus C, all of that, times F. That's it. For right now, this little expression, this is our entire universe. Everything we're about to build, every complex idea, it all starts right here with understanding this one line. Now, here's the question. The one question that this whole field is built on. If we take the value of A and we just nudge it a little bit, what happens to L? How much does L change? This might seem simple, but I promise you, answering this single question is the absolute key to making a machine learn. And to answer it, we need a new way of thinking about numbers. All right, section 2, the language of influence. See, to answer our question, we need more than just a calculator. We need to invent a special kind of tool. One that doesn't just give us the final answer, L, but also remembers exactly how it got there. A system that can track influence through every single step of the calculation. So instead of that boring line of text, let's visualize it. Let's build what's called a computation graph. Look at this. It's like a map of our expression. Each number is a little bubble, a node, and every operation, the plus, the multiply, is a connection between them. You can literally see the data flowing forward. See how A and B come together to make E? And then E and C combine to make D, all the way to the end. This, right here, is the forward pass. It's just the calculation, but drawn out. Okay, so how do we actually build this graph in code? We invent a new kind of object. This is our star player, the value object. I want you to think of it as a superpowered number. It doesn't just hold its data, like the number 5. It also remembers its underscore children. It knows how it was made. And it has this extra empty slot called grad. This little object is the fundamental atom of our entire system. So about that empty grad slot, this is the whole point. This is where we're going to store the answer to our big question. The gradient, or grad, is the language of influence. It's a single number that tells you exactly how sensitive the final output, L, is to any value anywhere in the graph. If a node's grad is positive, it means making that node's value bigger will make L bigger. Simple as that. Okay, so the big question is, how do we actually calculate the grad for every single one of these nodes? We need to fill in all those empty slots. Well, we do it with this really beautiful, almost magical process called backpropagation. And here's the key. We start at the end. We start at L and we flow the influence backward through the graph. The influence of L on itself, well, that's just 1. So we set L.grad to 1 and we begin our journey backward. So how does this backward flow actually work? It all comes down to the chain rule from calculus, but let's forget the scary math symbols. Think of it like this. The gradient that's flowing back from the output, that's the upstream gradient. It's the influence coming at you. Then each little operation, each plus or multiply sign, has its own local derivative. Think of that as how much that specific operation on its own amplifies or shrinks the influence passing through it. So the new gradient for any node is just the upstream gradient times its local derivative. That's it. That's the whole secret. And here's where it just clicks. Look at the math from multiplication versus the code. In calculus, we say the derivative of E with respect to A is just B, right? So the local influence is just the other number in the multiplication. And the code? It's literally that. A.grad gets the upstream gradient from E times B.data. The abstract math of the chain rule becomes one single, beautiful line of code. It's awesome. And what about addition? It's even simpler. The local derivative of an addition is just 1. It doesn't change the influence at all. It just passes it straight through. So you can think of a plus sign as a gradient router. It takes the upstream gradient and just copies it, distributing it to all of its inputs. The influence just flows right through. Okay, let's take a breath. We've invented this powerful value object that knows how to track influence through additions and multiplications. We have our building blocks. Now, let's use them to assemble something that actually starts to look like, well, intelligence. Let's build a neuron. Seriously, a neuron isn't some magical, mysterious thing. It's not. If you crack open the neuron class in the code, what do you see? It's just a very specific, carefully arranged collection of multiplications and additions. That's it. It's exactly the kind of computation that our value object was born to handle. So what does a neuron do? It takes some inputs, x, it scales each one by a weight, w, it adds a single bias, b, and then it squishes the whole thing through an activation function, like tanh. But here's the kicker. Every single one of those weights and the bias, they are all value objects. And what does that mean? It means after this neuron fires and gives us an output, we can backpropagate through the entire thing and find out precisely how much every single weight and bias influence that final result. Okay, now for the real aha moment. We figured out how to calculate the influence of every knob and dial in our system. So, what do we do with that information? We use it to get smarter. This is it, the core learning loop.
And it's a simple 4-step dance. You ready? 1. Forward pass. You make a prediction. 2. Calculate loss. You see how wrong you were. 3. Backward pass. You call dot backward to find out why you were wrong, calculating all the gradients. And 4. Update. You nudge every single parameter in your network just a tiny bit in the right direction. This dance, repeated thousands of times, is learning.
I love this quote because it's the perfect mental picture. A parameter's gradient is literally a little arrow pointing uphill. It's pointing in the direction of more error, of higher loss. So what do? We just take a tiny little step in the exact opposite direction. That's all gradient descent is. It's just walking downhill. Let's make this super concrete. Look at this parameter p. Its value is negative 3.0. After the backward pass, we find its gradient is a positive 2.0. What does that tell us? It tells us that increasing p will increase the loss. We don't want that. So in the update step, we multiply the gradient by a small negative number, our learning rate, and add it to p. The result? The new value is negative 3.1. We've nudged the parameter in the direction that should, in theory, reduce the loss next time. We got a little bit smarter. Okay, so our engine is awesome, right? It's elegant, it's intuitive, but it's a teaching tool. It's a bicycle with training wheels. So why can't we just scale this up and build something like ChatGPT with this exact code? Let's talk about where it breaks. So here are the big problems. First, it's slow. Painfully slow. We're processing one number at a time in Python loops. It's also naive. Simple gradient descent is like walking downhill blindfolded. You can get stuck in little valleys really easily. It can be fragile. Bad initial weights can cause the whole thing to blow up. And fundamentally, this scalar, one number at a time approach just does not scale. It's way too expensive for the massive networks we use today. But here's the cool part. Understanding why our simple engine breaks is the perfect motivation for the next layer of ideas you're going to encounter in deep learning. These aren't just random new topics. They are direct solutions to the problems we just identified. So what's the biggest, most important next step? It's this idea of vectorization. Instead of processing one number at a time in a slow Python loop, production engines like PyTorch and TensorFlow process entire matrices or tensors of numbers all at once. They do this on specialized hardware like GPUs, and the speedup isn't just a little bit, it's a massive, game-changing difference. And that leaves us with one final provocative thought. We've been acting like learning is just walking down a simple, smooth hill. But what if it's not? What if the lost landscape is a complex, winding valley with cliffs and weird local minimums? Is walking straight downhill always the best path to the bottom? Asking that question is what leads you to discover advanced optimizers, smarter ways to initialize your network, all the cool stuff. But the best part is, now, you have the fundamental intuition to understand exactly why all those things are so necessary.